Today we will start a new chapter, that is feedback amplifier. Okay. Feedback amplifier, the reference book is Sedra and Smith, and this is chapter 10. We have discussed little bit about feedback while studying the common source amplifier. We have studied source degeneration and we talked about negative feedback, right. So, today we will discuss about little bit of different type of feedbacks and what are the different type of feedback amplifiers that we can use. So, we all know that negative feedback is degenerative and positive feedback is regenerative. So, what is the meaning? In negative feedback our gain is reducing, and in positive feedback what is happening? Our gain is increasing. So, if your gain is increasing, it may happen that it can become unstable, right. So, in positive feedback, although your gain is increasing, but you will be seeing that most of the time we are only using this negative feedback, because it helps to stabilize the circuit. Okay. In positive feedback what happens? It keeps on increasing and it goes to saturation or it becomes unstable. But there is a particular application of positive feedback. Can you tell me where it is? Positive feedback is used in a particular circuit. Any idea? Oscillator. Okay. So, this positive feedback is used in oscillator where the oscillation starts without any input. In oscillator generally we do not have any input. So, what happens? This positive feedback keeps on building the noise, okay, and when it reaches a certain amplitude and frequency it locks. Then this feedback path is cut and it sustains the oscillation. So, there is a particular circuit of positive feedback and oscillator that we will study later. Today we will focus more on negative feedback. So, we all know that there are certain advantage of negative feedback that we have also seen, right. In source degeneration amplifier, what is the advantage? One is gain is little bit reducing, it becomes more stabilized, and the dependency on beta or GM, that is getting reduced. So, what is the meaning? That this negative feedback, it desensitize our sensitivity is little bit reduced, right, because if we think about beta or GM, these are technology parameter, right. So, as a designer you have no control. So, if you have no control, so your open loop gain you have no control, right. Now, in negative feedback what is happening? That your gain is dependent on some resistance ratio, right, that is the feedback factor. So, feedback factor that you can choose. Okay. So, these are all written here. Okay. Desensitize the gain is less dependent on the technological parameter like beta, threshold voltage, etc. It reduces the nonlinear distortions, makes the gain constant, controls the input and output resistance. The input resistance and output resistance, that is also affected by this negative feedback, it gets increased or decreased, and we will see that it actually helps. It reduces the effect of noise, it extend the bandwidth of the filter, and thus it helps to use for high frequency applications. It increases the stability. So, these are the many advantages of negative feedback. Positive feedback we only use in oscillation. So, this is a general feedback structure. So, what is a general feedback structure? I have a source, I have an amplifier, this is my amplifier, right. This is my main open loop amplifier, okay, and this is my feedback element, okay. Generally mostly it is passive element, maybe resistance, capacitor, etc. But this is my active amplifier. So, this is my structure. So, in open loop what you have, between input and output you have no control, this is straight, right. In feedback what you are doing, you are taking a portion of the output and getting it subtracted or added in the input side. So, that is feedback, right. We are taking the customer feedback and some of this we are using to make better the supply chain or product chain. So, same thing like that. So, we have an output and in this open loop we have no control. Now, in closed loop what we are doing, we are taking a portion of this output by a element and that portion is again getting added or subtracted at the input side. So, this is our general feedback structure. So, if we draw this, suppose this is your A, this is your xi and this is your say V0 and say this is your feedback factor, say this is your xf and say this is your xs. So, what is your V0? Xs into A, right. What is your xs? Xi is added plus and feedback is minus. So, this is xi minus xf, xf is your feedback factor. What is xf? This is your V0 into beta. Okay. So, let us do it again. This is my input, input is going to an amplifier, amplifier gain is A and this output is going to a feedback element beta and getting subtracted from the xi. So, xi minus xf is equal to xs and if we multiply xs into A, that is our V0, okay. And if we multiply V0 with beta, that is our xf. So, these three are my equations, right. So, if we write again V0 is equal to xi minus xf into A is equal to xi minus what is xf? Beta V0 into A. Now, you take this V0 one side, what will become 1 plus A beta is equal to xi into A. So, what is your V0? Xi by A by 1 plus A beta. So, what is your gain? V0 by xi is your gain, right, or this is A, you can tell closed loop gain. A was your open loop gain, this is closed loop gain, right, is equal to A by 1 plus A beta. So, now you think little bit, previously my gain was only A, now I am dividing it with 1 plus A beta. So, A is large or small? A is large. So, I am dividing a gain with a large element. So, my gain will, my closed loop gain will, which kind of feedback? Why negative? Because this sign is negative. You can do the opposite just at home, you just try just the opposite, you make this symbol plus, then what will happen? This will become A by 1 minus A beta. So, one interesting thing let us discuss, say for positive feedback, our gain will be closed loop gain, this gain please do not get confused, this A it is my open loop, suppose a op amp, nothing connected. So, its gain is open loop gain whatever, that is my A. The moment I am connecting it in a output and input, I am connecting with some element, that is become closed loop. Okay. So, in positive feedback you can do the math and you will find that it is 1 minus A beta. Now, one interesting phenomena can happen. You just think that the moment at some frequency it may happen that A beta is equal to, right. So, what it will become? Infinite gain. So, that is used in oscillator actually. We choose this beta factor such a way that A beta becomes 1, and at which frequency it becomes 1, the oscillator will oscillate at that frequency. Okay. We will discuss this later, do not worry. So, it is clear this mathematics. So, that is drawn here. This is a general structure. So, what is the meaning? This is my say op amp, okay, and this is the feedback element, whatever the resistor you connect na, positive input or negative input connections are there, right, inverting and non-inverting op amp. So, this is your main op amp and the resistance connections from output to input is beta. So, do not get confused with this beta with the beta of BJT, this is just the feedback factor. Okay. This is a some resistance ratio or capacitive ratio, whatever the element will be there, the gain of that is beta. Okay. Generally it is less. Clear? So, what we are doing? The way we did x0 is equal to, here the terminology are little bit different, I have used some little, they have used xs here, I have used xi there. So, those you, I hope you will understand. Okay. So, finally, if we come to the closed loop, it will be A by 1 plus A beta, that is important and you know how to derive that, right. Now, one important thing is that suppose your A is quite large. So, A beta terms should be much greater than 1, right. So, your A, if you neglect 1, it becomes A by A beta, it becomes. So, you see in closed loop your A terms is not there, understood. Now, is it advantage or disadvantage? Let us just discuss this. Suppose you have an op amp, right. So, I have an op amp, this is open loop, what is my gain? A is roughly ideally infinity, right. So, that is your amplifier. So, ideally my open loop gain is infinite, right. Now, my question is, can you use that as an amplifier? This is an amplifier, right, op amp, amp means amplifier. So, my question is, can you use it in open loop as it is? I give you a op amp as it is, just a positive terminal, negative input terminal and output and power supply will be there. So, my question is, I ask you, suppose I gave you a 1 millivolt, I ask you to make it a say 9 volt. Can you do that with this op amp? What will happen? I give a say sine wave. Okay. So, my structure is like this, positive input I give this Vi, negative input I make it ground. So, it will compare, positive will compare with what? Which voltage? This negative input is 0. So, it will compare with 0, right. The moment Vi will be above 0, output will go to what voltage? Plus what? there is a plus VCC and minus V, you know that, right. So, the moment this difference is positive, this gain is infinite, it will multiply it with that, it will go to what voltage? Can it go to infinite voltage? It cannot go. It will go and clamp to which voltage? Plus VCC. So, it will behave like what? Square wave. Getting my point? The moment Vd is greater than 0, our output will be V0 will go to plus VCC, that is we call it will go to saturate, and the moment Vd is less than 0, V0 will go to the other direction, right. This is what is this? What is this V0? V0 is equal to Vd into A. If Vd is positive, it will go to plus VCC. If Vd is positive, it will go to VCC. If Vd is negative, it will go to negative maximum possible voltage. It will not go to infinity, it will try to go to infinity, but it will clamp at VCC and clamp at V. Clear? This concept is clear. Why? Why this is happening? Because your gain is infinite. So, it will try to move towards the highest possible, and what maximum you can give output. Your output is defined by this na power supply. So, you cannot output cannot go beyond this, you are not generating, you are just amplifying, right. But is it amplifier? What is the first characteristics of amplifier that we discussed? Linearity. It should look like same, right, but does it look like same? I have a sine wave, if I want to amplify it, it should be also a sine wave, right. If it is not, then what we will say, that other nonlinear elements are superimposed and distortion will come, right. So, what are the nonlinear element? So, if your output is a linear function of input, right, y is equal to mx, up to that first order term it is linear. The moment other higher order term will come, right, it will start to get non-linear. Okay, up to first order term it is okay, it is linear, superposition theorem will be satisfied, right. So, I gave you an open loop, please understand this, this is important. So, you will understand a basic question, that why we use feedback in op amp. I have designed an open loop amplifier, this is an amplifier, but in open loop can I make it an amplifier? No, it becomes like a compare, right, comparator. In open loop it behaves like, say, it compares, right, with what it compares? This could be your Vref, you can tell this is my reference voltage. The moment my input goes above reference voltage, it is plus, just like a digital logic, right. You can say this is logic 1, this is logic 0. So, logic 1 means you can say, okay, my input is higher than my reference voltage you can decide. Instead of 0 you can make it a say 1 volt, you can make it a 2 volt, it is your choice, your requirement, and it becomes a comparator. The moment this goes, this 0 is a DC, right, that you can change, understood. So, if I change it, suppose rather than 0, if it is now x, so the moment it will cross x, then I will get a 1, clear. So, that is one problem of open loop amplifier. Now, my next question is, what happens in closed loop? in closed loop you see, if this is a positive, this is my V I and this is my R 1 and R 2, you know the output V 0 is equal to, this is non inverting, right, 1 plus R 2 by R 1 into V I. Agree? Now you see, can you see any A term here? Op amp open loop gain is A. Can you see any A term here? No, na. So, now what is your gain? If you neglect 1, roughly R 2 by R 1, right, 1 plus R 2 by R 1. Suppose R 2 by R 1 is 9. So, 9 plus 1 is equal to 10, 10 is your gain. So, from infinite you are coming to a finite value, right. Now, my question is, then why you designed an op amp, why you took pain to design an op amp with a gain of infinite, means very large gain. You are using a very finite gain and that is not that large. Now, why you take a pain to design an amplifier with very high gain? Can you answer me? Question, is it clear? Control the gain, which gain? Closed loop gain. What will happen if A is not infinite or A is not large? No, my question is, see, we are neglecting this. If A is very large, then only we can neglect, right. If A is not large, then this approximation is not proper. That is why we make A very large, so that in closed loop we can easily neglect the open loop portion. If we do not make this A very large, okay, then what will happen? This some effect of A will be there. We are actually considering that some error we are considering, right. A real figure is something else, but we are approximating so that we can cancel out this A term. Clear? So, why we are making this open loop gain very large? So that this figure, this one we can neglect, so that A beta much greater than 1, this conclusion we can arrive, and our percentage of error here, actually this is not our true gain, right, this is, you see, approximate sign is there. So, my percentage of error will go down. The more A will be large, the less will be the error, right. That is the only relation. That is why we are making open loop gain very large. But if you think that, okay, in negative feedback we are not actually increasing the gain, we are actually decreasing the gain, but making it controllable, very well defined. So, same way you see this. So, this structure now behave like a feedback structure. So, you see this block diagram, I have an A, I have an feedback element. So, you see this structure, this is my 2-port network of an amplifier that we did in amplifier section, right. This is a model. So, this is my input side, this is my amplifier side A, this whole is, we will consider like a block of A, but if we draw the 2-port network, it will be like this, right. Input side is V, output is a dependent voltage amplifier with A into Vi, that is it. And from the output you are taking a, from the output to the input. Now, you will be saying that how the input are connected. Input is actually your Vd, right, differential, this is a differential. So, you see output is coming to the input, your input is not single ended, our op amp I have 2 input. So, this connection you see it is coming from plus input and minus input. So, a portion of the output is now coming to the input side. And how this is coming? how this voltage, this is the voltage, right, that we are subtracting with this voltage. So, what is this voltage? This voltage is Vs. So, what is this node voltage? This will be also Vs, right, no current flows. Input impedance is op amp input impedance infinite. So, I is equal to 0. So, if no current flows, whatever Vs is here, that will come over here. Now, my question is, what will be the voltage here at this node? This is a subtraction, right, Vd. Vd is equal to V positive minus V negative. Okay. So, what is this Vf? This feedback factor, this voltage Vf or Vn. This voltage is V0, right, this voltage is V0, and what connection I am having? This is a R2, this is a, so what it becomes? Potential divider. So, what will be this voltage? R1 by R1 plus R2 into V0, that is it, right. So, my Vs is, input is Vs and feedback factor is V0 R1 by R1 plus R2. So, what is the ratio of this? Vf by V0 is equal to R1 by R1 plus R2. This is my feedback factor, beta. Beta means the portion of voltage that is coming to the input divided by the portion of output voltage, okay, and that becomes R1 by R1 plus R2. Now, if you get the beta, you can put it directly in the equation. What is your equation? A by 1 plus A beta. You put it there and you can approximate, neglect 1, A gets cancelled and your gain is 1 plus R2 by R1, that you did in op amp class actually. Okay. But that is not a true expression. True expression, some A component will be there, but we are neglecting it considering our ideal open loop gain is very large. But if it is not true, then in this equation some component of A will come. Okay. Clear, up to this clear? So, just quickly recap what we discussed: positive feedback, negative feedback advantage, it is making desensitized, right. The dependence on the technology parameter are reducing, gain is reducing, that we agree, but it tends to stabilize the circuit. It helps to the input impedance or output impedance, it modifies such a way that it helps actually, that we will check later. And also the frequency, the bandwidth you know, every amplifier it works up to a certain range, frequency range, that is called bandwidth. This negative feedback also helps to increase that range. Okay, we can improve the bandwidth also. So, that we will see, and that is the structure. Our negative feedback is closed loop gain is A by 1 plus A beta. In case of positive feedback, it will be just opposite, it will be A by 1 minus A beta. And we also discussed that how in case of op amp this structure can be useful. And we also discussed that why open loop op amp is not useful in as an amplifier, it is useful as an comparator, not as an amplifier. Now, this is what we are talking about, okay, the gain desensitivity. We understand that gain is reduced and the dependency on the, suppose a delta change happens at the feedback factor, then how much it will affect my output, that is sensitivity, right. Sensitivity is change in a delta change in the input, how it will affect your output. Okay. So, they have defined it like delta AF by AF, and that is actually this is very small. So, we can tell that closed loop actually improves our desensitizing our gain. That means, if there is any variation, that will not affect the output, output will be more close to the constant, right, that we want, right. Next is bandwidth. So, actually this is where we are interested, where the gain is constant, right. This is our amplitude and this is our frequency, and this is our lower cutoff, this is our higher cutoff, FL, Fi, and this difference we call as bandwidth, right. It FL could be 0, okay. And if we can push this higher and higher, advantage is that we can use this amplifier in high frequency application also. Suppose one amplifier is usable up to 10 megahertz, another amplifier is usable up to 1 gigahertz. So, 1 gigahertz obviously is better choice, right, but it will be more costly and you have to take care of designing that amplifier, right. So, that you can use. So, the 1 gigahertz amplifier you can use it for 100 megahertz, you can use it for 500 megahertz. So, you have your choice or your options is wide, right. So, it is a better choice. So, this negative feedback, so this was our open loop characteristics. In closed loop characteristic, this blue one is our closed loop. In closed loop, what we know? Gain is reduced. So, our amplitude gain is getting reduced, but by doing so what happens? My bandwidth, you see, bandwidth now expand, clear. I have the same plot, now I am reducing this open loop gain. So, what happens? Previously my bandwidth was up to this, now my bandwidth is increased, is not it? So, this negative feedback, it helps in expanding the bandwidth. Okay. So, how to prove that? Instead of just A, you write A by 1 plus S tau. Okay. This A that was constant, we are considering, previously gain was constant, right, we are taking that no frequency element is there, but in that A we are considering okay, some frequency element we are putting inside that. So, how to do that? First order equation, A by 1 plus j omega r c, right. If we have a R and C, what is the equation? Something like that, right. Some j omega term will come, right, that j omega you can replace with Laplace S, clear. So, this A we are just replacing with A by 1 plus S into some omega factor, right. So, this omega will now might define my cutoff frequency, clear, and we will put this into A by 1 plus A beta form. Okay, do not get confused. Our equation is A by 1 plus A beta, that is simple, that you know. Now, in this A, we will modify this A as M by 1 plus S into, say here they have written omega h. So, that we will replace, and then we will do the multiplication on all these things. Then we will see that this modified, that omega h, that will be multiplied with 1 plus A beta. Okay, you do that and you reorganize the structure and your equation will be modified like this. So, what is the meaning? The factor by which my gain was reduced, by the same factor my cutoff frequency will be increased. that we are not doing anything, we are just putting it in a equation and we are flattening that equation. Okay. We are doing the calculation and then we are seeing this structure like this, and we are seeing that this, because of this equation, our 1 plus s into this omega factor is now multiplied with 1 plus a beta. So, what is the meaning? My 3 dB frequency is increased by the same factor, the gain was reduced. Now, we have 4 basic feedback configuration. These are voltage amplifier, current amplifier, and transimpedance amplifier and transconductance amplifier. Okay. So, in this voltage amplifier, what is my input side? Voltage or current? Voltage. What is my output side? Voltage. Okay. So, voltage amplifier, both my input side is also voltage, output side is also voltage, right. Now, what I want to do? I want to take a portion of this output voltage. Okay. So, you see, if you want to take a portion of this output voltage, how we will take it? What is this connection? See, take it easy. If you have a parallel connection, this upper node voltage is same or different? If you have a parallel connections, the voltages are same, right. So, this is your V1, this is your V2, and that is true for this parallel connection as well as this parallel connection. So, this parallel connection, what you tell? Another terminology? Shunt, right. So, this is your shunt network. So, if you want to sample the output voltage, so what way you can do that? Shunt, right, this is parallel. And if you want to suppose add to voltage, how you can do that? Series. So, this output voltage you want to subtract from the input side, the connection should be what? Parallel, it is same, right? It should be in series, clear. But if you want to subtract, then it will be minus and plus, that the connection will be just change. So, this is his input side is in series. Think again, voltage amplifier, input side voltage, output side voltage. From the output I want to take a portion of the voltage, right. So, how we can do that? Shunt. So, output side is shunt, input side I want to subtract or add depending on my configuration. This is a negative feedback, I am subtracting. How we can do that? Connection should be series. Okay. So, this voltage amplifier is also known as voltage mixing, voltage sampling. Where you are mixing? Input side or output side? Input side you are mixing. Mixing means addition or subtraction. Sampling, output side. Sampling means what? You are taking a sample. So, this voltage amplifier is also known as voltage mixing, voltage sampling. Take care of the notations. Okay. Voltage mixing, input side mixing, voltage sampling, output side sampling. This is also known as the series shunt feedback. Series is at the input side, shunt is at the output side. So, same amplifier, the main amplifier is named as voltage amplifier, same is known as voltage mixing, voltage sampling. Same is known as series shunt feedback amplifier. Clear? So, you do not need to remember this, you just try to understand this. Okay. What we are doing? I have a voltage amplifier, input side is voltage, output side is also voltage. I am taking off the sampling a portion of the output voltage, that is shunt, and I am subtracting. So, this is series. So, this is a series shunt voltage feedback amplifier. What is your main amplifier? This is your main amplifier, that will be A, right, and this is your feedback network, that is we will model like a beta. This is an example we did, right. So, same way this is an example. The non-inverting amplifier, that is an example of a voltage amplifier. Input side is voltage, output side is voltage. I am taking a portion of the voltage and subtracting at the input side. Clear? So, this is an example of a series shunt. Input side you see it is in series, output side you see it is in parallel. It is parallel, that is why I am taking a potential divider, right. So, now this A will replace with a model. What model we know? 2-port network. Similarly, this beta, this will also replace with a 2-port network. What was our amplifier 2-port network? Input side, input impedance generally, voltage amplifier input impedance infinite, right. So, no connections. Output side, there will be a dependent voltage source, that is the 2-port, right, ideal 2-port, if we neglect all the input resistance or output resistance. Output side output resistance is 0, right. So, this is our ideal 2-port network. So, that we will put here. Clear? So, in beta you see we have put the exact same thing, but in a flipped way, right. This is my input for the feedback network, for the main amplifier this is my input, right. For the feedback network this is my input, this is my output. This is flipped, right, you understand that. Feedback network, this it is taking this as an input and giving this as an output. Amplifier, this is taking this as an input and this is as output. Feedback is, I have to draw the opposite flipped way. Okay. And in the main amplifier, if I consider a input impedance, I will draw a Ri. If I have an output resistance, I will draw a R0, that is drawn. So, do not get confused by this structure, it is as simple as that block. Okay. This is just that block. Now, what we are doing? Inside those block, we are putting another model. First, we have modeled that with only A. Next, we are modeling this A with its equivalent 2-port network. So, for first day, we will stop up to this, and in next class, we will try to concentrate on this and see. We already know that our gain will be, that we already know, that we will try to check with this complete circuit, and we will also try to check what is our input impedance and output impedance, that closed loop, open loop, whatever open loop impedance was there, Ri and Ro, how they are getting modified. and we will see that this 1 plus A beta there will be multiplied by Ri or divided by Ro. Input impedance for voltage amplifier, higher is better, right, infinite input impedance is better. So, this negative feedback will help us to increase this and help us to reduce this. So, they will be actually helping, this negative feedback also helping in terms of input impedance, that we will verify in next class. Okay. So, we are closing at that point.